The date was April 8, 1941, at 2:35 in the afternoon. A vast aircraft began its movement down the runway at Nakajima's testing site outside Tokyo. This machine was immense, exceeding 100 feet in length, with a wingspan approaching 140 feet. Four engines roared to life, pulling it into Japan's heavy, humid atmosphere. Engineers from the Imperial Japanese Navy watched, their expressions taut with anticipation. 18 months had gone into constructing this bomber. $950,000 had been spent acquiring the American airliner on which it was based. A fabricated crash had been staged to conceal their true intentions. Now, finally, their creation was aloft. The pilot advanced the throttles. The aircraft climb was sluggish, far too slow. The engines strained audibly against its mass. Controls felt heavy, unresponsive. Something was fundamentally amiss. An underlying issue had always persisted. The Japanese had taken foreign technology, reverse-engineered the world's most advanced transport, hoping to transform it into a strategic bomber capable of reaching targets across the Pacific. Instead, they had produced one of aviation history's least effective heavy bombers. This account describes how Japan acquired an American airliner, commercially rejected, and transmuted it into a spectacular failure. It is a narrative of covert operations, elaborate deceptions, engineering overconfidence, and the perilous assumption that mere replication equals true understanding. The story originates not from the advent of war, but from the prosperous era of American commercial aviation. The year was 1935. Air travel was rapidly reshaping America. Airlines expanded their networks. Passengers grew increasingly confident in flight. Aircraft manufacturers engaged in intense competition to build the next generation of airliners. Douglas Aircraft Company had just launched the DC-3, which was destined to become the most commercially successful aircraft of its time. Yet, even before the DC-3's operational debut, airlines were already contemplating larger possibilities. William Patterson, president of United Airlines, presented Douglas with an ambitious concept. He sought an aircraft that would quickly make the DC-3 seem antiquated. Patterson envisioned a four-engine airliner capable of traversing the entire continent without intermediate stops for fuel. It would carry 42 passengers during day flights or 30 in sleeping berths for transcontinental overnight journeys. Pressurized cabins would allow flight above adverse weather. Air conditioning would ensure passenger comfort. It aimed to incorporate aviation's absolute pinnacle of technology. The proposal was daring. No airline had ever operated a four-engine land plane for scheduled passenger service. The technology Patterson described was barely nascent. Constructing such an aircraft would necessitate resolving engineering challenges never previously tackled. The risks were enormous. The financial outlays would be staggering. However, the potential gains were equally compelling. The developer of the first successful four-engine airliner would establish dominance in commercial aviation for a generation. Douglas found the concept intriguing but approached it with caution. They understood the endeavor would push their capabilities to their furthest limits. They agreed to proceed only if other airlines demonstrated interest. American Airlines swiftly committed. Eastern Airlines joined the consortium. Pan American Airways and Transcontinental and Western Air, the latter becoming Trans World Airlines, also pledged participation. Each airline contributed $100,000 toward development, establishing a $500,000 fund to support this most ambitious commercial aircraft undertaking. The engineering task proved formidable. Douglas assembled a design team led by Arthur Raymond, who had previously managed the DC-3 program. This team faced unprecedented problems. How could a wing be built both strong enough for four large engines and light enough for efficient flight? How would landing gear be designed to support an aircraft weighing over 60,000 pounds? How could fuel lines, hydraulic systems, and electrical wiring be routed through a fuselage also requiring passenger comfort? Questions multiplied as the design progressed. How to pressurize a cabin at high altitude without inducing structural stress that would cause metal fatigue. how to supply sufficient auxiliary power for air conditioning, cabin lighting, and galley equipment without overloading the electrical system, how to train pilots to operate an aircraft twice as heavy and complex as anything they had commanded before. The team labored for 2 years. They generated 8,100 drawings, documenting every facet of the aircraft. A detailed wind tunnel model was constructed, undergoing 866 separate tests over 1,100 hours. They analyzed airflow, stability, and control effectiveness at speeds and altitudes no previous airliner had achieved. 1,300,000 rivets were used to assemble the prototype. The total engineering investment amounted to 500,000 man-hours, an unparalleled expenditure for a commercial aircraft. The result was unlike anything witnessed before. Douglas simply named it the DC-4. The aircraft showcased innovation throughout. It was the first large aircraft to feature tricycle landing gear, meaning it sat level rather than resting on a tail wheel. This seemingly minor change carried significant implications. Passengers no longer ascended an incline to board or descended one to exit. Cargo loading became simpler. Ground handling was more predictable. The aircraft possessed a modern appearance because its design was truly contemporary. The nose wheel configuration would eventually become industry standard, but in 1938, it was groundbreaking. Its wing was massive, stretching over 138 feet from tip to tip. This scale was necessary to generate enough lift for the aircraft's weight while maintaining acceptable takeoff and landing speeds. The wing design evolved from the proven DC-3, scaled up dramatically. For Pratt & Whitney are 2180 Twin Hornet engines, each producing 1,450 horsepower, were mounted on the wings. The engines were positioned with a noticeable toe, angled slightly outward. This unusual setup aimed to enhance stability by creating beneficial yaw moments during single-engine operation. The tail presented perhaps its most distinguishing feature. Instead of a single vertical stabilizer common to most aircraft, the DC-4 incorporated 3 vertical fins, one centrally and one at each end of the horizontal stabilizer. This unique configuration stemmed from a practical necessity, illustrating commercial aviation's operational limits. The aircraft size meant a single conventional tail would render it too tall for existing hangars at airports nationwide. Airlines could not afford new hangars at every destination. The triple tail kept overall height manageable while providing adequate directional control. This was an engineering compromise dictated by financial realities. Inside the fuselage, the DC-4 was conceived to deliver unparalleled luxury. The cabin, wider than any preceding airliner, allowed for more comfortable seating. Passengers occupied chairs truly resembling furniture, not the utilitarian benches of earlier aircraft. A standard configuration carried 42 passengers, but Douglas also developed sleeper variants with fold-out berths for overnight flights. Passengers could board in New York, dine, sleep in a proper bed, and awaken in Los Angeles. Air conditioning maintained cabin comfort regardless of outside temperatures. The design even included provisions for cabin pressurization, though this system was not fitted to the prototype. The flight deck also featured advanced technology. Power-boosted flight controls lessened the physical effort to fly the large aircraft. Without this assist, control forces would have been too heavy for precise landing or maneuvering. An alternating current electrical system supplied reliable power for instruments and systems, unusual for an era dominated by direct current. Auxiliary power units offered electrical and pneumatic power on the ground, removing the need for external ground equipment at remote airfields. On June 7, 1938, the DC-4 prototype prepared for its inaugural flight. The location was Clover Field in Santa Monica, California, site of Douglas's principal factory. At the controls sat Carl Cover, Douglas's chief test pilot and one of America's most esteemed aviators. Cover's career strikingly paralleled the advancement of modern commercial aviation. Born in 1893 in Pennsylvania, he learned to fly in the Army during World War I. He became a test pilot post-war, joining Douglas in 1930. He had piloted the first flights of the DC, one in 1933, the DC-2 in 1934, and the DC-3 in 1935. He had, in essence, personally guided the development of the aircraft that made commercial aviation feasible. Now he added another milestone. Cover meticulously completed his pre-flight checks, his decades of experience having taught him that thoroughness averted fatal surprises. The four engines started sequentially, each twin Hornet awakening with its characteristic rumble. The aircraft, registered NX 1810 with construction number 1601, taxied toward the runway. Ground crew members observed, a mix of pride and apprehension etched on their faces. 2 years of their dedication were about to face judgment. Cover advanced the throttles, and the immense aircraft began to accelerate. The DC-4 was heavy, consuming significant runway before reaching flying speed. At the correct airspeed, Cover gently pulled back on the control column, and the aircraft ascended into the Californian sky. The most advanced airliner ever constructed had just made its successful first flight. The flight lasted approximately 45 minutes without incident. Cover landed, reporting the aircraft handled reasonably well, though some characteristics required further investigation. Testing continued through the remainder of 1938. Douglas pilots assessed handling at various speeds and altitudes. They tested performance in climbs, descents, and turns. They examined the reliability of its complex systems under repeated operational stress. As with all new aircraft, problems arose. Some systems did not function as designed. Performance figures sometimes fell short of predictions. The type certificate was delayed while issues were addressed. On May 5, 1939, the Civil Aeronautics Authority finally granted approval. The DC-4 was officially certified for commercial use. The prototype was then transferred to United Airlines for in-service evaluation. This was the critical juncture. Would the DC-4 prove a breakthrough or a disappointment? Controlled test flights were one thing. Daily airline operations, with paying passengers, strict schedules, and maintenance limitations, were an entirely different challenge. On June 9, 1939, a remarkable occurrence linked the DC-4 to aviation's origins. The aircraft was in Dayton, Ohio, a city deeply significant to American flight, being the hometown of Wilbur and Orville Wright. Carl Cover brought the DC-4 to Dayton for demonstrations, and a distinguished passenger boarded for a flight over the city. This passenger was Orville Wright himself, then 67 years old. Orville had been just 32 when he and his brother made the initial powered flights at Kitty Hawk in 1903, a flight that lasted 12 seconds and covered 120 feet. Now, 36 years later, Orville sat in the cabin of a four-engine airliner capable of transporting 42 passengers across the continent. He surveyed the city of his youth, where he and Wilbur had built their first flying machines, where the bicycle shop funding their experiments still stood. The flight bridged generations of aviation progress. The airplane's inventor was now flying in its most sophisticated form. Cover later described it as a pinnacle of his career. A photograph of Wright in the DC-4's cabin became an enduring image. Yet, despite successful test flights in this symbolic moment, United's evaluation soon revealed profound issues, jeopardizing the entire program. The DC-4 was excessively complex for practical airline operations. Its advanced systems demanded specialized maintenance capabilities that most airports lacked. Mechanics, trained on simpler DC-3s, were baffled by the DC-4's electrical networks, hydraulic circuits, and control mechanisms. Operating costs escalated far beyond projections due to the time and expertise needed for upkeep. The aircraft consumed fuel at alarming rates. Its four engines guzzled gasoline faster than anticipated. Range was less than promised, as fuel consumption exceeded design estimates. Performance fell short across almost every category. A situation worsened after seating capacity increased from 42 to 52 passengers to improve economics. That change pushed gross weight to 65,000 pounds, far above its original design. The fundamental issue was weight. The DC-4 had grown heavier throughout development, as engineers added systems and strengthened structures to resolve emerging problems. Every solution seemed to add more mass. Engines deemed adequate for a 50,000-pound aircraft now struggled with 65,000 pounds. Climb performance was poor. Cruise speed was disappointing. Range remained insufficient for the transcontinental missions it was designed to accomplish. One by one, the sponsoring airlines delivered their verdict. Pan American and Transcontinental and Western Air had already withdrawn before the initial flight, instead investing in the Boeing 307 Stratoliner, a smaller, less ambitious, but functional aircraft. Now, United, American, and Eastern reached the same conclusion. The DC-4, though technologically impressive, was unsuitable for commercial service. It was too costly to operate, too complex to maintain, and too unreliable for scheduled flights. Douglas faced an embarrassing and expensive failure. Years of work and approximately $3 million of their own money had been invested in an aircraft no one wished to purchase. The DC-4 prototype remained at the factory, a burdensome monument to overambition, a drain on company finances. The consortium airlines paid Douglas $91,250 each to settle their commitments, a mere fraction of development costs. Douglas executives confronted the dilemma of their unproductive asset. The solution took two forms. First, Douglas would begin anew, designing a fresh four-engine airliner based on the hard lessons of the DC-4's shortcomings. This new aircraft would be simpler, lighter, and more practical. It would employ proven Pratt & Whitney, or 2,000 engines, abandoning the problematic Twin Hornets. A conventional single vertical tail would be adopted, accepting the height penalty for simpler construction. It would eliminate the complex systems that had caused so many issues. Pressurization would be reserved for a later model. Power-boosted controls would be simplified. The aircraft would retain successful features like the tricycle landing gear and basic wing design, while discarding troublesome elements. Second, Douglas sought to sell the original prototype, hoping to recover some development costs. Finding a buyer for a rejected airliner would be difficult. Any technically sophisticated entity would surely know its problems. Yet the alternative was scrapping the prototype and writing off the entire investment. Douglas began quietly marketing the DC-4 to any potential buyers. That buyer emerged late in 1939 from an unexpected source. Representatives from Japan's Mitsui Trading Company approached Douglas with a proposal. They wished to acquire the DC-4 prototype for Japan Airlines, known as the Nippon Koku. This airline was rapidly expanding with Japan's growing empire, requiring modern aircraft for routes across Asia and the Pacific. The DC-4, despite its American service issues, represented technology far exceeding anything available in Japan. Japanese aircraft manufacturers had never built anything of such size or sophistication. Douglas saw an opportunity to mitigate their losses. The Japanese offered $950,000, a significant sum to offset some development costs. To Douglas executives, the transaction appeared straightforward: a foreign airline buying an American commercial aircraft for civilian purposes. There was nothing illegal or unusual. American manufacturers regularly sold aircraft abroad. Export controls on commercial aircraft were minimal. Douglas saw no reason to decline. What Douglas did not know, and what the American government did not know, was that Japan Airlines was not the true buyer. The airline served as a front for the Imperial Japanese Navy. The Navy had observed American aviation for years, particularly its four-engine aircraft. Japan's industry excelled with single-engine fighters like the Zero and twin-engine bombers like the G4M Betty, but lacked four-engine design experience. True strategic bombers, capable of Pacific crossings, demanded four engines. Distances were too vast for twin-engine aircraft with useful bomb loads. American B-17 bombers demonstrated four-engine capability. The Imperial Japanese Navy desired this for themselves dreaming of striking American bases across the Pacific, even the continental United States. But Japanese engineers lacked the knowledge to build such an aircraft. The DC seemed an almost too good to be true solution. Here was the most advanced four-engine aircraft globally, available commercially. Its American rejection was deemed an American problem. Japanese engineers believed they could enhance the design with their own engines and modifications. They would acquire the aircraft, study its construction, uncover its secrets, and apply that knowledge to build their own bomber. The Imperial Japanese Navy approved the plan, arranging financing through Mitsui Trading Company. Japan Airlines became the public face of the transaction. On September 29, 1939, Douglas factory workers in Long Beach, California, disassembled the DC-4 prototype and loaded it onto a freighter bound for Japan. The aircraft was meticulously crated, treated with the same care as any valuable customer delivery. Alongside the physical machine, Douglas provided all accumulated engineering data: drawings, specifications, test results, performance data, and maintenance manuals. Everything Douglas knew about the DC-4 went into those crates. Even the wind tunnel model, used for 866 tests and showing every modification, was included. A team of Douglas technicians traveled to Japan to aid reassembly. They arrived at Haneda Airport near Tokyo in early 1940, commencing work to ready the aircraft for flight. Japanese engineers watched every step intently. They inquired about assembly, component functions, and Douglas's design decisions. The Americans believed they offered normal customer support, unaware they were instructing potential enemies in strategic bomber construction. When reassembly finished, the DC-4 wore Japan Airlines' emerald green and silver livery. It was Japan's largest, most advanced aircraft. Newspapers featured photographs. Airline executives posed beside it. The wind tunnel model, painted identically, was prominently displayed at Japan Airlines headquarters. The airline announced its magnificent new aircraft would soon begin service on prestigious routes. However, the DC-4 never transported a single paying passenger for Japan Airlines. Almost immediately after reassembly and a few verification flights, it was quietly transferred to the Nakajima Aircraft Company, as directed by the Navy. Nakajima had a contract to develop a long-range heavy bomber, designated the experimental Type 13 attack bomber. Specifications demanded a minimum 3,000 nautical mile range, sufficient for Pacific targets. The DC-4 served as their foundation. The Japanese government needed to explain Japan Airlines' flagship aircraft's sudden disappearance. They could not admit military transfer, so they invented a cover story. In mid-1940, Japanese press reported the DC-4 had crashed into Tokyo Bay shortly after takeoff from Haneda. The aircraft was declared lost, nothing recovered. No further statements would be made. This story was pure fabrication. The DC-4 had not crashed. It sat in a Nakajima hangar, methodically dismantled by engineers documenting each component. The fake crash served multiple objectives: explaining public disappearance, preventing U.S. intelligence tracking, providing cover for the Navy's secret program, and discouraging inconvenient questions about a vanishing airliner. At Nakajima, engineers focused intensely. They measured every DC-4 dimension. They analyzed structures and systems. They weighed components. They traced wiring and hydraulic lines. They created detailed drawings of Douglas design parts. They photographed everything from multiple perspectives. The aircraft was essentially reverse-engineered to its smallest detail. What emerged from this study was the Nakajima G5N, which the Navy designated the experimental Type 13 attack bomber. Nakajima named the aircraft Shinsen, meaning deep mountain in Japanese. This name evoked massive strength, imposing presence, and unshakable permanence. The Japanese hoped their new bomber would embody these qualities against American targets. The G5N borrowed heavily from the DC-4. The wing was largely identical, with the same platform, structure, and engine placement developed by Douglas engineers. The tricycle landing gear was directly copied, giving the G5N identical ground handling advantages as its American ancestor. Overall size and configuration closely followed the DC-4. From certain angles, their family resemblance was clear. But the fuselage was entirely redesigned for military purposes. Where the DC-4 had a passenger cabin, the G5N featured a long ventral bomb bay, carrying up to 4,000 kilograms of bombs, roughly 8,800 pounds maximum, or 2 aerial torpedoes for anti-shipping strikes. The bomb bay's flexibility allowed varied weapon loads. The nose was reshaped with a glazed compartment for the bombardier, providing aiming visibility. The cockpit was higher and further back than on the DC-4. Defensive armament bristled from multiple positions. Two 20mm Type 99 cannon provided heavy firepower, one in a power dorsal turret and one in a tail turret. Four 7.7mm Type 92 machine guns added lighter defense in the nose, ventral, and waist. The DC-4's distinctive triple tail was replaced with a twin fin arrangement, more conventional and easier to manufacture with Japanese tooling. Fabric-covered control surfaces followed standard Japanese practice. The aircraft was designed for a crew of 7 to 10 men, depending on mission. For power, Nakajima chose their own NK-7A Memori engines, rather than attempting to copy the American Pratt & Whitney design. The Memori was an ambitious 14-cylinder air-cooled radial, later described by the Smithsonian as the most powerful 14-cylinder engine ever built. Each Memori was supposed to produce 1,870 horsepower, a significant improvement over the 1,450 horsepower Pratt & Whitney Twin Hornet engines in the original DC-4. The Japanese reasoned that more powerful engines would compensate for the additional weight of military equipment. If American engines proved inadequate for the DC-4's weight, more powerful Japanese engines would surely solve the problem. Only about 200 Memori engines were manufactured between 1941 and 1944, reflecting the difficulties in producing such an advanced design. The first G5N prototype was completed in early 1941. It stood as an impressive sight on Nakajima's test facility ramp. Over 100 feet long, with a wingspan of nearly 140 feet, it dwarfed all other aircraft Japan had ever built. Navy officials inspected their new bomber with evident pride. Japan, they believed, was finally entering the era of four-engine strategic aviation. On April 8, 1941, at 2:35 in the afternoon, the first prototype began its maiden flight. Imperial Japanese Navy observers watched anxiously as the massive aircraft slowly climbed from the airfield. Japan's first four-engine land-based bomb, was airborne. The dream of striking across the Pacific seemed reality. However, test pilot reports soon shattered that dream. The G5N was heavier than expected. The Memori engines failed to deliver their promised power. The theoretical 1,870 horsepower rarely materialized. Engines ran rough, requiring constant adjustment. They overheated during sustained climbs. Reliability was poor, with frequent failures forcing aircraft grounding for repairs. Flight controls felt sluggish and unresponsive compared to smaller Japanese aircraft. The G5N handled not like a fighter or even the twin-engine Betty bomber. It handled like what it truly was, an overweight converted airliner straining against design limits. Performance numbers confirmed pilot reports. Maximum speed reached only 261 miles per hour at optimal altitude, significantly slower than contemporary American or British heavy bombers. The American B-17 could cruise faster than the G5N's maximum speed. Both British Lancaster and Halifax bombers were faster and carried heavier bomb loads. Its service ceiling, just under 25,000 feet, limited its ability to fly above enemy fighters and anti-aircraft fire. Climb rate was poor, demanding extended time to reach operating altitude. Most critically, range fell short. The G5N could fly about 2,600 miles, well under the 3,000 nautical mile minimum the Navy specified. The Navy had sought a bomber for targets across the vast Pacific. They received an aircraft that could barely reach the nearest enemy bases and would be vulnerable throughout its mission. The dream of bombing Pearl Harbor or striking the American mainland was impossible with the G5N. It simply could not fly far enough with its weapons payload. Nakajima proceeded with additional prototypes, hoping refinements would resolve the issues. The second prototype flew. Engineers adjusted engine cowlings, propeller pitch, and fuel systems. Performance improved slightly, but remained far below requirements. A third prototype incorporated further changes, then a fourth. Each aircraft demonstrated the same fundamental flaws. The Mamori engines continued their problems. They overheated during climbs. They vibrated excessively at certain power settings. They failed at inconvenient moments during test flights. Nakajima engineers were forced to detune the engines to improve reliability. Running the Mamori at lower power settings reduced mechanical stress and decreased failure rates, but also reduced the already inadequate power output. Performance problems worsened further. The G5N was trapped in a vicious circle. Engines lacked power for adequate performance, yet pushing them harder caused failure. Reducing power for reliability made performance even more inadequate. In a desperate attempt to salvage the program, Nakajima built 2 additional prototypes with different engines. These G5N2 variants used Mitsubishi 4 billion Malawian kwacha's Kase engines instead of the troublesome Mamoris. The Kase was a proven, reliable engine, powering the successful G4M Betty bomber and other Japanese aircraft with thousands of dependable operational hours. But the Kase produced only 1,530 horsepower, significantly less than even the D-rated Mamori. The G5N was already underpowered with engines theoretically capable of 1,870 horsepower. With only 1,530 horsepower, performance became truly dismal. The G5N2 flew even slower than original variants. It climbed even more poorly. It offered even less range. The more reliable engines made the aircraft safe to fly, but utterly incapable of its mission. By 1942, the program's verdict was unanimous. The G5N Shinsen was a failure. No engine swap, no modification, no refinement could overcome its fundamental problems. The aircraft was simply too heavy for any available Japanese engine to propel it adequately. The Navy had spent years and immense resources developing a bomber that could not bomb. The Imperial Japanese Army also briefly expressed interest in the G5N. The Army and Navy, bitter rivals who rarely cooperated, both recognized the value of a 4-engine bomber. The Army proposed 2 design variants, the Ki 68 and Ki 85, which would use different engines for Army requirements. A full-scale mock-up of the Ki 85 was actually constructed in 1942, incurring considerable expense. But the Army watched the Navy's struggles with the G5N and wisely decided against repeating their mistakes. Every problem the Navy encountered, they realized, would apply equally to Army variants. The weight problem was fundamental to the design, insoluble by any engine change. The Army canceled its variants in May 1943, without producing a single flying aircraft. The mock-up was scrapped. Resources were redirected to programs with better prospects of success. The Navy canceled the bomber program, but refused to completely waste the aircraft. 4 of the 6 G5N prototypes, 2 original G5N1 variants with Mamori engines, and both re-engined G5N2S with Kase power plants, were converted into long-range transports. They were redesignated G5N2L and named Shinsenkai, meaning Deep Mountain Modified. Bomb bays were removed or sealed. Offensive armament was deleted. Defensive armament was reduced. The crew was cut to just 6 men. These aircraft were assigned to the 1021st Kokutai, a naval air transport unit based at Katori Air Base. This unit became the sole operator of all 4 surviving Shinsen aircraft. For the remainder of the war, these 4 Shinsen transports flew supply missions across the Japanese Empire. Their long range, A legacy of the DC-4ES transcontinental design made them valuable for reaching distant garrisons inaccessible to smaller aircraft. They hauled spare parts, medical supplies, and military equipment to isolated outposts. The mighty bomber, intended to instill terror in American hearts, spent the war as a mere cargo plane. The aircraft, costing $950,000 in years of development, became a glorified freight hauler. American intelligence eventually detected the G5N's existence through aerial reconnaissance. Photographs taken from high altitude showed the large four-engine aircraft at Japanese airfields. Intelligence analysts at the Allied Technical Air Intelligence Unit in Australia studied the images carefully, identifying the type as a heavy bomber. Following the naming convention developed by Captain Frank M. McCoy Jr. in mid-1942, they assigned the aircraft the Allied code name Liz. Under this system, Japanese bombers and transports received women's names, while fighters received men's names. The irony was profound. The Allies assigned this code name anticipating a dangerous strategic bomber, unaware that Japan had abandoned that mission years earlier. American commanders prepared contingency plans for Japan, potentially using Liz as a strategic bomber against Allied positions in the Pacific. That attack never materialized. The Americans did not realize Japan had already discarded the G5N as a combat aircraft years before. The threat they prepared for was hollow. The imposing four-engine bombers they photographed were, in fact, just transport planes conducting cargo runs. The Allied intelligence assessment was not incorrect, merely incomplete. The Liz was indeed designed as a bomber. It was simply too flawed to fulfill that role. Carl Cover, the test pilot who had guided the DC-4E on its inaugural flight and taken Orville Wright for a memorable ride over Dayton, did not live to witness the war's conclusion. When America entered the conflict after Pearl Harbor, Cover returned to military service at the request of General Henry Arnold, commander of the Army Air Forces. Cover was promoted to colonel and assigned to oversee B-29 Super Fortress production at Bell Aircraft's Georgia factory. He brought the same meticulous professionalism to wartime manufacturing that had defined his test flying career. His aviation contributions were extraordinary. He had piloted the first flights of the DC-1, DC-2, DC-3, DC-4E, and DC-5, essentially ushering in modern commercial aviation with his own hands. On November 27, 1944, Carl Cover died at age 51 in a plane crash during a snowstorm near Dayton, Ohio. He did not live to see victory over Japan Day or to learn the ultimate fate of the DC-4E he had tested. A street at Long Beach Airport was later named Cover Street in his honor, a modest remembrance for a man who profoundly shaped aviation history. Lawrence Bell, founder of Bell Aircraft, remarked of Cover that no single individual in the aircraft industry had contributed more to commercial and military aviation. None of the 6 G5N aircraft survived the war. The 4 transport conversions flew until they were destroyed, worn out, or scrapped. Japanese records from the final, chaotic months of the war are incomplete, so the exact fate of each aircraft remains unknown. Some may have been annihilated by American air attacks on Japanese airfields. Others might have been cannibalized for spare parts, as Japan's industrial base crumbled under Allied bombing. By the time Allied forces occupied Japan, no complete G5N remained. The aircraft persists only in photographs, technical drawings, and the recollections of those who built and flew it. The Douglas DC-4E prototype was stripped bare by Nakajima's engineers and reduced to components. Whatever remained after all useful information was extracted was likely scrapped for materials as Japan's wartime shortages grew desperate. The wind tunnel model, once painted in Japan Airlines colors and displayed as part of the deception, may have survived the war, but its current location is unknown. It might now sit forgotten in a Japanese museum storeroom, or it may have been destroyed during the firebombing campaigns that devastated Japanese cities in 1945. The full narrative of the DC-4E and the G5N did not emerge until after Japan's surrender in August 1945. Allied investigators, scrutinizing Japanese aviation programs, uncovered documents describing the Shinsen program and its origins. They learned of the DC-4E purchase, the fabricated crash story, Nakajima's reverse engineering efforts, and the disappointing flight test results. The intricate deception that had hidden the program from American intelligence before the war was finally laid bare. The irony of the situation was profound and instructive. The United States had rejected the DC-4 because it was too complex and expensive for civilian use. Japan had purchased it, intending to weaponize American technology against America. Instead, the Japanese inherited all the DC-4's inherent problems and compounded them with their own new difficulties. The same fundamental flaws that rendered the DC for a commercial failure also made the G5 a military catastrophe. Douglas grasped the DC-4's flaws because they had endured the arduous development process. They understood which design decisions had caused problems and why those choices were made. They knew which alternatives had been considered and rejected. They possessed institutional memory, accumulated over decades of aircraft development. When they designed the successor aircraft, they could avoid their previous mistakes. They retained what worked and discarded what did not. Nakajima lacked this crucial context. They could observe what Douglas had constructed, but they could not perceive the underlying rationale. They did not know which features were reluctant compromises. They did not understand which systems had created endless difficulties during development. They could not identify which specifications had proven impossible to meet. They saw only the finished product, not the agonizing process of trial and error that shaped it. This knowledge gap proved fatal for the G5N program. When the Memori engines underperformed, Nakajima lacked the experience to swiftly diagnose and rectify the issues. Japanese engine development had not yet attained the level of American or British engineering. When the aircraft proved overweight, Nakajima failed to comprehend the cascade of decisions that led to its mass. When performance fell short, they could not intelligently modify it because they insufficiently understood the original design's intent. Meanwhile, Douglas applied the severe lessons of the DC-4's failure to create a superior design. The redesigned DC, for that appeared in 1942, was essentially a new aircraft, retaining only the name and the core concept of a four-engine transport with tricycle landing gear. It was simpler, lighter, and far more practical. It utilized proven Pratt & Whitney R2000 engines. It featured a conventional single vertical tail, accepting the height penalty for simplified construction. It eliminated the complex systems that had caused so many problems. The U.S. military designated this new aircraft the C-54 Skymaster and ordered it in vast quantities. Over 1,200 aircraft were built during the war, making it one of the conflict's most produced four-engine aircraft. They formed the backbone of American military air transport, flying cargo and personnel across the Atlantic and Pacific Oceans. President Franklin Roosevelt used a specially modified C-54, nicknamed the Sacred Cow, as his personal transport. After the war, they supported the Berlin airlift, delivering supplies to the blockaded city in one of history's greatest humanitarian operations. Many were converted for civilian use, serving airlines worldwide for decades. The design that had failed as the DC-4E succeeded brilliantly in its revised, simplified form. The lesson of the DC-4E and the G5 in Shinsen extends beyond aviation history. Technology cannot be wholly appropriated. The physical object is merely one aspect. The underlying knowledge, the hard-won experience that forged it, the institutional wisdom guiding its application. These intangible factors cannot be created and shipped overseas. Japan spent $950,000 to acquire the DC-4E. They invested years reverse engineering it and developing the G5N. They built 6 prototype aircraft. In the end, they possessed nothing more than 4 cargo planes and a profound lesson in the limitations of technological imitation. Douglas learned from the DC-4E's failure and created one of history's most successful transport aircraft. Japan copied the failure, producing an even greater failure. The G5 in Shinsen, the Deep Mountain, was meant to cast its shadow across the Pacific, granting Japan the power to strike American territory. Instead, it became a historical footnote, a cautionary tale about the limitations of imitation, proof that merely copying another's work is no substitute for genuine understanding.